So hello, welcome to another day of physical science. Today we'll start chapter 6, which is called Waves and Sound. Basically, we're going to talk about what waves are. Not necessarily water waves, although they would work the same, but sound waves, light waves, and waves on a string or any other device. But just in general, what that all means, how we can edit it, and things like that. What a wave is the motion of a disturbance. What it is that if I throw something, if I threw something across the room, that would be the motion of whatever I threw. But when you talk about a wave, what it is let's say I take this string here, and you know what? Let's how do I do that again? Oh, my video is over. That's why. If I go and bring one side up, what happens is the disturbance of a piece lifted, that's what moved. Is that in doing this, I'm not necessarily moving any of the dots to the right or the left. That if you look at this first green dot here, it's at some set location. And when I lift this up and bring it down, it stays at that location. What's happening is the disturbance is moving. And that although none of the things are moving to the right, we see movement to the right because that is where the disturbance moves. Now, a mechanical wave like that requires three things. First is some sort of disturbance. So I'm going to do this with the string instead. That if I'm going to do a wave down the string, like so, I need some sort of disturbance. I need my hand to go up to start the wave. If nothing ever happens, it'll stay still. If you think of like a pond of water, that if nothing touches it, it'll stay flat. You throw a rock in, waves will ripple out. It needs something to start it. It also needs a medium to be disturbed. That if I go like this, I can make a wave in this string. If I do this, you don't see a wave. I need something to be disturbed and something to have the wave in. I think there's mechanical waves. Light waves will kind of break this, but we'll come back to that. And also the pieces need to be connected. That if I take a string here and start moving it up and down and have another piece of string sitting somewhere else, it may not have a wave in it. The pieces have to be connected. That if you separate them and have no connection, the wave will not propagate. What a wave really is, when you get down to it though, is the propagation of energy without the propagation of matter. If a wave, I just love this GIF because it's so weird, but when the wave goes past this pizza, the pizza does not go to the left or the right, it goes up and down. And when something goes up or down, that's potential energy. That once again going to this, when I lift this up, and let's put this in slow motion, what happens is each piece is gaining potential energy for a little bit, and then it's going back to no potential energy because it's going up in height. And so the energy is moving across, just not the physical movement. Now, you're probably most familiar with waves in water because that is the easiest place to see them. But you can also have waves in solids. An earthquake is a wave in solid. And honestly, me doing this to a string is a wave in solid. You can also have waves in gases. Sound is a wave in gas. Right now, you can hear me speaking because, well, if you're not using headphones, well, even if you are using it, either way, there is a speaker that is vibrating. And that vibrating speaker is causing the air molecules to vibrate. And that is a sound wave. It is a type of wave that you are translating to be sound. Are we making sense so far? Now, so far, the type of wave I've been showing, this guy, that really if I just set this going, and let's go back to normal speed, and just keep it going continuously, this is what is called a traveling wave. It's called a traveling wave because it looks like everything is moving to the right. And if I just stick to the pulse, you can kind of see it obviously that just one goes across. But yeah, with the oscillation, you can see it travels over. That's what a traveling wave is. You got a string, you flip it, the thing moves across, that's a traveling wave. The pulse moves at a set speed. And you know what? Let me see if I can just shrink this window down to show everything. The pulse moves at a set speed. So when I flick this, I can say how quickly that piece moves. And even if I do this, I can say how quickly everything's moving to the right. And yeah, as I said, this is called a traveling wave. There is definite movement to the side. Once again, though, the materials itself isn't moving. This beaded thing, none of these beads are moving to the right. They're only moving up and down. The disturbance is moving to the right. Now, traveling waves come in two flavors, transverse and longitudinal. What you've been looking at so far is a transverse. When this thing is going, a transverse wave, the movement is perpendicular to the displacement. What I mean is that this wave is moving, the disturbance is up and down, but the up and down is moving to the right. It's perpendicular to each other. Light is a type of transverse wave. A longitudinal wave is one where the disturbance is in the same direction as the of the movement. If I take a slinky and kind of push towards it and make it bounce back and forth, that's a longitudinal wave. What you have is you have areas where it's more compressed and areas where it's less compressed, known as rarefacted or rarefaction. And you can have it going bouncing back and forth. But a longitudinal wave is one where the what is displacing is parallel to the motion. I'll eventually have a better GIF of this, explaining it a little better for a longitudinal wave when I talk about sound, which won't be till Wednesday anyways. But for today, I'm mostly going to do transverse waves, which once again is this guy. Okay. Now, looking at our transverse wave, we can define a whole bunch of terms. And the first two I'm going to start with are amplitude and wavelength. Amplitude is the max height from this middle to the highest point. That we start. Nope, I want oscillate play. That amplitude is literally how big the wave is. Small amplitude, the wave doesn't go very high. Big amplitude, the wave goes very high. Amplitude is, God damn my mouse. Amplitude is just the distance from the 0 point to however high the wave is. In this case, that would be the amplitude. Amplitude uses the symbol capital A and is usually measured in meters. It's related to the energy of the wave, but isn't quite that. Note, it is not from the highest point to the lowest point. That is not the amplitude. It's from the middle to the highest point. And so yeah, big amplitude, oops. Come on. Or small amplitude, that's the difference. Now you'll note when I change this amplitude, let me pause this, is that I can look at this and say the distance from peak to peak, from here to here, and I'm going to put this in slow motion again, has some set value. And that when I change the amplitude, that distance is the same from peak to peak. That distance, how far you are from highest point to highest point or lowest to lowest point, is called the wavelength. And the wavelength would literally just be the distance from here to there. And as the wave travels, that will be a constant. And as you can see that, yeah, the distance from that to that hasn't changed. If I start messing with the amplitude, still hasn't changed. I can change it. Let's see, this will change it. I'm trying to think about it. So this is a short wavelength or a longer wavelength. Here's a very short wavelength, but it's just how far from peak to peak. Wavelength uses the symbol lambda. Lambda is a Greek symbol, looks like an upside down Y. That's lambda. And wavelength is traditionally measured in meters. It's just how far that distance is from peak to peak. The last term you need to know is frequency. Before I can talk about frequency, I want to talk about period. Period, which is measured with capital T, is how long it takes the wave to travel the distance of one wavelength. What I can say, I can do it with this GIF here, but I want to wait till it hits 20. 19, 20. Is right now this dot was at the 0 point of this wave. And I can time how long it takes this dot to return to the 0 point traveling in the same direction. And I can see that for it to go up, then down, then back to the middle, it's taking this, well, how this thing reads, the GIF is a little slow, of 20 seconds. That is the period. The period is how long it takes the wave, and we'll go slow motion again. So if I look at this, nope. If I look at this green dot, it would be how long it takes I'm looking at the leftmost green dot, well, the leftmost on the wave. I can say, and here I'll draw it, looking at this one, how long it takes that dot to return to that spot moving in the same direction, where it goes down, up, back down. That is the period. That would be measured in seconds. And it is just how many seconds in a cycle. The frequency, on the other hand, is the inverse of that. To find the frequency, frequency is 1 divided by period. Well, frequency uses the symbol F. And its units is therefore inverse seconds, but that gets its own name. It's called hertz. And so period 1 divided by the period will always be the frequency. And it's how many cycles in a second. It simply says how many times does it go there and back in 1 second. If you say something has a 60 hertz frequency, like electricity, in AC electricity, frequency is how quickly electrons go there and back. When you say something is 60 hertz, that means it goes there and back 60 times in 1 second. But it's just the inverse of the period. Okay? Now, logically, wavelength is the distance the wave is, and frequency is how quick it goes up and down. We know distance over time was one of our velocity equations. What this does is we can say that the velocity of a traveling wave, how fast this thing is moving to the right in this case, will simply be the wavelength over the period. But since 1 over period is frequency, we can say the velocity of any traveling wave, how quickly it moves to the right, is frequency times wavelength. If I start changing the wavelength, I change the speed of the wave. And let me go back to normal. Where this guy's moving pretty fast, where this guy's moving much, much slower because he has a much, much smaller wavelength. Wavelength goes up, speed goes up. Wavelength goes down, speed goes down. Likewise, if I mess with the frequency, if the frequency goes up, wave goes faster. Frequency goes down, wave goes slower. Now, this general equation can be used for any type of wave, but it's derived from traveling waves. But in general, it works for most everything. Okay? Let's look at an example. When you play an instrument, and I have some tuning folks, I have a whole bunch of things. But when you play an instrument, different notes, like this right here is a D, which hopefully that sound is coming through though. But that's a D. This right here is an A. The difference in pitch is actually the frequency of the note. That this A had a frequency of 426 hertz, and the frequency of this D was 288 hertz. High pitch just means high frequency. And so when you have a high frequency thing, it just sounds higher to us. When we define what a note is, it's just set to a frequency. And so a middle G is 392 hertz. Now it's of noting that the speed of a wave, a speed of sound in air is 344 meters per second. And so my question is, if a middle G moves through the air at 344 meters per second and has a frequency of 392 hertz, what's its wavelength? What I did is I gave the velocity and the frequency. If you want the wavelength, velocity is wavelength times frequency. And if I divide both sides by frequency, I can get the wavelength by dividing out and getting a value. It's a direct relationship. Does that make sense? Any questions so far? Okay. So with this applet, I've been having it go out the window, literally. That the post just goes and goes on forever. But let's say I was to fix the end. What happens when you have a fixed end is when the wave hits the end, it bounces back. And if the end is fixed, it bounces back inverted. And so as long as when I make the one post, as long as there's no damping, we're not really going to talk about that, the wave will just bounce back and forth from end to end. If I said it, yes. Yeah.
You cut out for a second.
Oh, I did?
You know, from my internet shit.
Oh, okay.
But so I played guitar for a long time. So this is kind of cool. Like seeing how it actually works.
We're going to talk about it in terms of guitar a little bit.
Yeah, no, I was doing the wrong, I was doing chapter 6. I started that by accident for a while. Then I was starting on chapter 5. 6 first by accident. I don't know how. But so I got it. But
okay. Here's the thing. Is if instead of one little pulse and we bounce back, if we have a continuous wave, what'll happen is it'll keep bouncing back. And it'll kind of do some weird, ugly things, but if you get it just right, it'll kind of look like it's not a traveling wave anymore. Oh, I had it right for a second and then it went off. It's real hard to get it just right. What'll happen is if you have, when the wave goes and bounces, if you're at just the right frequency, you'll get to a point where the wave traveling to the left that is creating it and the wave traveling to the right will perfectly line up and give the appearance of a wave that isn't moving to the left or right, but just bouncing up and down in place. This is called a standing wave. Really, the standing wave is just two traveling waves, one going one way, the other going the other way. This GIF shows it a little better. Well, what I'm saying is I have this upper wave and this middle wave, and if I add those two together, I get the wave below. This is because waves follow something called the interference principle, and you can just add up the peaks. Now, for most frequencies, you're just going to get something kind of off and it just kind of looks weird. But if you have the exactly perfect right frequency, which really I should have gone and tried to solve for what it would be, but I didn't, you'll get this standing wave. That the wave will perfectly bounce up and down. But as I said, it is two traveling waves, so we can still talk about its velocity, even though nothing is actually moving, because we can talk about the velocity of the individual pieces that make it up. And we can still talk about the wavelength and frequency and amplitude. As I said, this is just when waves interfere with each other. Of note, when you have a standing wave, and you're going to be seeing this in the next lab, we're going to have things called nodes and antinodes. What it is when you have a standing wave, and you know what? Can I make a good standing wave on this thing? If I could, that would make my life so easy. No, I can't. Let me actually go back a slide, use this GIF. What I would say is a node is a place that isn't moving. This right here is a node because it's not moving at all. An antinode is a piece where the displacement is maximum. This other black dot is an antinode, because that's what's moving the most. And if you set a wave vibrating on a string, and these right here are pictures of a wave vibrating on a string, what it will look like is the area that's moving will just kind of be a solid, because it's just quickly moving through that whole thing. This isn't a big solid piece, but it's a string going from here to there to here to there to here to there very, 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 very quickly. And so we can look at where the antinodes and nodes are. Now, as I've been showing with my little applet, though, not all frequencies will make standing waves. That if I just pick a random frequency, I'll get beginning of one, but then it just does something else, then does that, then goes back. It just doesn't quite work. And what it is standing waves will only exist at very exact frequencies. These frequencies are known as natural frequencies, or more commonly, resonant frequencies. Where what frequency, and if you notice when I was trying to get a when I was trying to get the standing wave here, I was just going and messing with the frequency and then restarting it, is because there will be exact frequencies that a standing wave will occur. Where those frequencies are would depend on the mass of the string, the length of the string, and the tension of the string. We will come back to that. And anytime you are in a natural frequency or a resonant frequency, you are in resonance. When you are in resonance, you will have maximum energy transfer. And as I kind of mess with this here, let me make this a little smaller. What you'll find is when it is looking more like a standing wave, I'm closer to one, is that everything's moving a lot higher up and down. And when it's not looking closer to a standing wave, it was moving smaller before. That's because at a standing wave, you had resonance, things will get bigger. Oh, that's real close. I'm really close right here. And so here's my standing wave, it going back and forth because I was in resonance. Not quite right, but close. You can actually really see this with a pendulum. That if I take a pendulum and just move my hand back and forth quickly, not much will happen. But if I move my hand back and forth slowly, not much will happen. But if I move my hand back and forth at the exactly correct frequency, I'm going to get a huge amount of displacement. Because all that is I hit the resonant frequency, whereas slower and faster does not match, does not match the frequencies. Now, it's worth noting all structures can vibrate at a natural frequency. This is a bridge that wind is hitting it at the perfect exact frequency to be resonant frequency. True story, in 1850, a group of 500 soldiers walked across a bridge and they were marching at perfect time. And because they were marching at perfect time, they were marching at a very set frequency. They happened to hit the resonant frequency of the bridge, which caused the bridge to basically 100% fall apart, killing almost half of the soldiers. It's something you got to think about when you're making devices that are going to deal with any sort of things going over, is what are the resonant frequencies. And a lot of suspension.
This is terrifying. This is terrifying, seeing a bridge like this.
Yeah,
like
no.
I'm a construction residential.
Yeah. We now have ways to, the way to get around that if you're building is because, yeah, this is terrifying. You don't want this happening to your bridge.
I'm building
is that
houses.
They kind of, you kind of would go and mess with a way in the tensions to try to make to lessen how many resonant frequencies it can have, and try to hit something that naturally would not occur. That's your goal.
My brother's an engineer. That's him.
Yeah, that works. And that's the general idea. Now, if I'm going to talk about wave on a string, earlier someone mentioned guitar. The best way to show it really is with a guitar. However, my guitar is an Everton Tower and is a little too big to
camera.
So I bought a really cheap ukulele, which I don't know how to play. A stringed instrument like a guitar or my cheap ass ukulele, what it is we have a string that is suspended with a set tension or force between 2 points. That the string does go up here into the neck, but really it's stuck to go from this point to this point. And what it is that string has a set tension. Each string has a different thickness. That different thickness means different mass. And they have a set length, where the length is from right now heel to heel. Anytime you have a wave on a string, it'll have a set velocity. Sorry, say that again?
You were showing the ukulele like you're struggling.
Oh, yeah. So sorry, for some reason you keep breaking up slightly, so I'm having a slight.
I know, it's my headphones and my internet is shit.
Okay. So yeah, if it seems like I'm not quite answering your questions, because I'm just not 100% sure what you're saying, so I apologize. You can always send stuff in the chat too if I can't.
It's
if I
fair.
don't understand it. I'm trying. I really am. And so what it is if I put a standing wave on a string, we already said that for a standing wave on a or for a traveling wave on a string, the velocity of the wave is wavelength times frequency, which is going to be true. But here's the other thing, that if you have a wave on a string, that velocity will also be set as the square root of f over mu. In this equation, f is the tension, how tight the string is. If it's like just like literally how hard we're pulling it. If I go back to this guy, this diode down here is changing the tension. And if I make it from a very tight string to a not very tight string, I can really mess with how fast it's moving, because all that's doing is, yeah, changing f. Mu is known as the linear density. It is the mass of the string over the length of the string. Now on a guitar, there's something called harmonics. And I don't know my harmonics on a ukulele as well as I know my harmonics on a guitar. I don't know how to play a ukulele or a guitar really. But on a normal guitar, there'll be a spot with 2 dots. That 2 dots is at the 12th fret. And what that is the halfway point. And what it is when you strum a string on a ukulele, what happens is you create a standing wave. What happens is the second I strum this, I'm going to make a traveling wave that's going to move out from my hand outward in both directions, where it's going to reflect off the pieces and bounce back. And they're built in such a way to basically always hit resonant frequency. And so I'm going to get a standing wave that's just bouncing up and down in point. And actually what it is that standing wave I get will have a wavelength of twice the length, because this is an entire wave. And what I have is it bouncing between this and this, which is half a wave. And so when you just strum a guitar or ukulele, you're just making a standing wave where the wavelength is twice L. If you lightly place your finger at the halfway point, not like play the note, but just lightly put your finger to touch it, you can create a harmonic, which once again, the first harmonic in guitar is what the double dot is. For the ukulele, I'm pretty sure it's right at this first fret. And if I lightly put my finger there and touch it, I still get a note. Not as nice of a note.
So I have a question.
Yeah.
Guitar, is that like palm reading? Like when you play a note and you hit your palm with it and you kind of mute it as you go. So you guys get a full wave, I guess, and a standing wave.
Yeah, so openness is a full wave, yes. And if you're playing
Just
guitar normally, like you're playing this fret and you're actually pushing down all the way, you're pushing down like you normally would play guitar and not just lightly putting your finger, that would still be a wavelength of twice L. You're just changing L. But I'm talking if you just lightly put your finger.
Mm-hmm.
Is there more though?
No.
Okay, cool.
I know I'm hard to read.
Yep. And so what happens when you lightly put your finger is you get the harmonic. What that does is it forces a node. When you force a node, you create a wavelength that is L instead of 2L. And because the velocity is set, the velocity is the tension in this string, the length of the string, the mass of the string, and none of that's changing. If I start changing the wavelength, I change the frequency, since velocity is wavelength times frequency. And so if I go from an open note to lightly putting my finger, I get a different pitch because I change the wavelength, therefore I change the frequency. Thing is, that's not how people play guitars. You play guitars pushing fully down and playing multiple strings. This is going to be out of tune.
Play a few notes if you would like.
That's okay. I'll just keep messing with my out of tune ukulele because I'm only going to make the tuning worse. Trust me. See, on a guitar or a ukulele, the different strings have different thicknesses. That a guitar, it goes from the thickest to the thinnest. A ukulele is actually out of order. But what it is this string right here is much, much thicker than this one. This string here is much, much thicker than this string here. And when I play the notes of the thick one, I get a low note. When I play the string of the thin one, I get a high note. The reason is because thicker strings have more mass. Because it has more mass, that means mu is bigger. Now, F is the square root of, V is the square root of F over mu. And if mu is bigger, V is smaller. And so thick strings, if my guitar GIF on the bottom, that top string being the thick one, the bottom one being the thin one, is that literally the velocity of the wave on these thick strings will be slower than the velocity in these thin strings. And since V equals lambda F, I'm not changing lambda. Lambda is going to be based off the length of the string. And I just play these without pressing any frets. All I'm doing is I'm changing the frequency. I'm changing the velocity without changing the wavelength. That means the frequency needs to change. And the smaller V is, the smaller the frequency. And low frequency is low pitch. And so heavy strings, thick strings are low notes. When thin strings are high notes. Say it again?
Quick question. So you know how there's 12-string guitars?
Yeah.
So with those, I mean, I've played them. I know the strings are like next to each other.
Yeah.
Just thicker and thinner strings.
Yep. Yeah, a 12-string guitar, it's still sets of 6 with are really close to each other, but each 2 strings of slightly different masses, and they worked out the masses just right to be, I don't know exactly, but I'm pretty sure it'd probably be like the same note at a different octave or like similar notes just to get the sound you want. But yeah, that's what it is. It's two strings right next to each other with slightly different, with different thicknesses that have the different masses to get the exact comparison of notes you want.
Well, thank you.
This is how tuning works on a guitar. When you tune a guitar or a ukulele, what you're doing when you tone this thing is you are pulling the string tighter or looser. And so if I want to tune a guitar, if I tune it so that it's tighter, the note goes higher pitched. If I tune it so it's less tight, it's lower pitched. And that by messing with this, I can change the pitch. With changing the pitch means changing the frequency. The reason why is if you increase the tension in the string, you increase F. If you increase F, you increase V. I am not changing the wavelength. Once again, the wavelength is just twice the length of this string. As long as I'm not playing a note, that'll be true. And since I'm not changing the wavelength, that means I'm changing the frequency. The larger V is, the larger frequency is. And so when you make a string tight, it gets a higher pitch versus if you make it not so tight. A little thing popped up saying, "Are you playing music? Set up professional audio things." No, I am not playing good music. I am hitting a guitar string or ukulele string.
I just kind of have a comment. So on guitar, there's 200 pounds of pressure pulling from the bridge.
Yep.
From all the strings.
Yep. Yeah, and that 200 pounds of pressure, it's because pressure is force over area, like we talked about last chapter. So this equation is the force, not the pressure, but you can work out exactly what the force is if you know the cross-sectional area of the string. And it'll just be how hard it's pulling.
That's cool, though, because how the acoustics, at least, they have to be designed and engineered very well.
Oh, yeah.
Because they're light, but they have, like, the superstructure and such.
Oh, yeah. Even this guy, it's really crazy. Like, I can just see in all the stuff inside to keep it in shape.
Use bamboo on those, so that's nice. Or the nice ones. I have a $40 one.
This is like 20. And my actual guitar in my office is ancient and, well, sadly it's there.
I have 2 electrics and 2 acoustics.
Oh,
one of them is 50 years old. Is my dad's.
Now, when you actually play a guitar, you normally how you do different notes is by pushing down on frets. And that by going from here, oh, sort of two now, by going from here to pushing down this fret, I can do different pitch notes. The reason why is when you play a guitar, what you're doing, when you push down on a fret, is you're basically changing the length of the string. That as long as you don't have a fretless guitar, which is a whole other can of worms and kind of interesting, when you push down like here, for example, and let me get this close to the camera, what I'm doing is I'm making it so there's a spot where it's stuck. And what'll happen is the strings on this side will vibrate and the pieces on the other side won't. The harmonics, when you lightly touch, can vibrate on both sides. But if you push down all the way, only this side vibrates. What that means is when you play a guitar and you push down, you are changing the length of the string. If you change the length of a string, that'll change the velocity of the wave, since velocity depends on mu and mu depends on L. But it also will change the wavelength, since the wavelength of the the wavelength of the string, as I said before, was just twice the length. And so that when you play a note, you change the wavelength and the velocity. Now let's just talk about if I cut a string in half. If I play the fret that's right at the halfway point and go from this note to this note, what happens is your length becomes half as much and your wavelength becomes half as much also, which means your mu will change by a factor of L over 2. And if you plug your mu into your V equation, it means the velocity of the wave will change by a factor of the square root of 2. If you change, but while the velocity changes a factor of square root of 2, originally your frequency would be the old velocity over lambda. Your new frequency will be your new velocity over your new lambda, where your V changed by a factor of square root of 2 and your lambda changed by 2, which doing some math gives you that at the halfway, your frequency changes by a factor of the square root of 2. And so what happens when you play the guitar, when you push on the frets, you are changing the frequency and you hear different notes because when you hit these notes, you hear the different frequencies because you're changing the wavelength and the velocity, allowing you to make music. Questions? Okay. That is waves on strings. Almost everything here can be used for other types of waves. And we're going to talk about basically the rest of this chapter is we're going to talk about some special types of waves, mostly light and sound. And like you could say, yeah, we already did sound waves. We're doing this. This was not me doing sound waves. This was just how the string was vibrating. The thing is, this string vibrating vibrates the air molecules, creates the sound waves. You can hear different pitch sounds, different sound waves, because I'm changing the frequency these strings vibrate at. But we're going to talk the actual sound and light waves, or at least sound will be Wednesday. Today we're going to do light. Light is something called an electromagnetic wave. What a light wave is an electric field that's oscillating up and down, and a magnetic field that is also oscillating left and right, that are perpendicular to each other. And they oscillate at a rate that, yeah, they just bounce back and forth perfectly perpendicular. And they're just a traveling wave. You don't really get standing waves with light. Just like other traveling waves, we can talk about the wavelength, velocity, and the amplitude of these waves. Of note, the electric field and the magnetic field, where B stands for magnetic field for the record, will have the exact same frequency and amplitude as each other. For that reason, we normally just talk about the electric field to do one or the other. If you start messing with the frequency or wavelength of an electromagnetic wave, you can start changing the properties. And what this does is fill out the whole thing called the electromagnetic spectrum. You see, electromagnetic waves, E field and B fields, bouncing back and forth, they consist of visible light. Visible light, though, is just a range of set wavelengths / frequencies. We'll get to how they're related when we'll come back to that.
Is this Reggie Biv?
Roy G. Biv is just this bit in the middle.
Yeah. Okay.
Roy G. Biv is just this.
Oh, red. Yeah, okay.
from 400 nanometers to 700 nanometers. But it also, electromagnetic waves can do other things. Radio waves, which, by the way, radio waves includes Bluetooth and Wi-Fi. They're radio waves. Is the same thing as light, just a different frequency. Microwaves in an oven, same thing as light, different frequency. Infrared, ultraviolet, X-ray, gamma ray, they're all the same thing. They're just changing the frequency or the wavelength. They're related. Do I say this here? Yeah, I say in a few slides. Now, what we can see is from a wavelength of 400 nanometers to a wavelength of 750 nanometers, where 1 nanometer is 10 to the negative 9 meters. And when you look at different colors, like my shirt is green. My shirt is green because it's about 540 nanometer in wavelength, the light coming off of it. That when we see different lights as different colors, what we're seeing is just different wavelengths or frequencies. Once again, they're related. And so anything you see as red is around 750 nanometers. Anything you see as a dark blue is around 400 nanometers. That is what we view as color, is what is the wavelength or frequency of the light. Now, of note, one of the things I said all waves needed was a medium to move in. Electromagnetic waves do not. They are weird. They can move through a vacuum. But they're the only type of wave that can move through a vacuum. If you look at the spectrum, though, what you'll see on it is not white. My thing here just shines nice bright white light on stuff. White light doesn't really exist. White light is something our eyes interpret. You see, if I have some nice white light, what it is it's all the wavelengths at once. There's something called a diffraction grating, and that if we were in person, I'd be handing them to you. And what it would do is it will separate light to its individual wavelengths. And when I diffract white light, what I get is a nice rainbow from red to this dark blue. And we'll come back to not purple, dark blue in a second. Because what it is white light is just a mixture of all wavelengths shined at the same time. I want to see how this works. Here's my diffraction grating. And so if I put this diffraction grating in front of this camera, you can start seeing like little bits of rainbow coming if I have it just right. It's because what I'm doing is I'm taking the white light and splitting it. Most light sources put multiple colors together to make a nice band.
Question?
Yes.
So, like, when we were younger, we had the hose and the spray at the sky, and it would make a rainbow.
Yeah.
Is that
exact same thing?
Okay.
I'll talk about a rainbow in more detail in a few more chapters when I talk about light in more detail. But it's the same thing. You're diffracting into the separate bands. That's what a rainbow is.
Thank you.
Okay. Now, as I said, white light does not really exist. White light is just a combination of all colors. Light only goes from red to dark blue. Purple light does not exist. Pink light does not exist. Now that might seem weird because you might be familiar with you can shine a purple light or a pink light on something. Why that is? What's the time? Let me see how long these videos are.
7 minutes.
1, 2. Yeah, it's gonna get a little tight. I'll come back to this if I have time at the end of the class today. But the short version is we can mix colors to get very exact things. 7 minutes. I can do it. I'll do it. So why you can see pink light or purple light when, as I said, they don't exist. Here is why. Let's start with pink.
We've all been told that the colors of the rainbow correspond to different wavelengths of visible light: red, orange, yellow, green, blue, and violet. Where's pink in that list? It's not there. There's simply no pink light. So where does pink come from? It turns out that pink, or magenta, fuchsia, or whatever you want to call it, is actually a mix of red and blue light. Light from both ends of the rainbow that our brains see as one single color. If you try to roll up the rainbow to make a color wheel, there'll be a gap between red and violet. That's where all of the rest of the light in the universe is supposed to go. Radio waves, microwaves, infrared, ultraviolet, X-rays, gamma rays, and so on. But since we can't see any of those wavelengths, we replace all that hidden grandeur with pink. And speaking in terms of light, pink should probably be called minus green, because pink is just the leftovers of white light when you take out the green.
So that's what pink light is. Purple light, on the other hand, is a little more complicated.
The rainbow as we know it is red, orange, yellow, green, blue, violet. Roy G. Biv. I'm ignoring indigo because, let's be honest, indigo? But where exactly is violet? Is it at the end here? This dark blue? And what's this brighter light blue-green? Cyan, perhaps? So why don't we say the rainbow is red, orange, yellow, green, cyan, blue? Roy G. Well, we actually do, and we've just forgotten. When Isaac Newton originally observed a rainbow of light split by a prism and made his labeling of the colors as red, orange, yellow, green, blue, indigo, violet, the thing he called blue was indeed what we would now call blue-green, or teal or cyan, reminiscent of the color of the blue sky. And what we now tend to call blue, Newton called violet, as in roses are red, violets are blue. Dark blue. He only included indigo in his fundamental 7 colors of the rainbow so that they would match the number of notes of the Western musical scale. Do, re, mi, fa, sol, la, ti. Yeah. Purple, magenta, and hot pink, as we know, don't occur in the rainbow from a prism, because they can only be made as a combination of red and blue light, and those are on opposite sides of the rainbow, nowhere near overlapping. So there is no purple or hot pink in the rainbow from a prism. Violet is there in the roses are red, violets are blue sense, but purple is not. So then why do rainbows in the sky often look like they have purple in them? I suspect sometimes it's an optical illusion whereby nice deep blues in small amounts surrounded by a lighter color appear purplish to our eyes. However, sometimes purple and pink really are there, because a rainbow is really a rain disk. Each color of sunlight reflects back in a bright rimmed disk, all of different sizes, which together add up to make a white disk with a colorful rim. But because light is a wave, interference from the raindrops themselves actually gives each disk multiple rings. The familiar outer ring is just the brightest. The others are called supernumerary rings, and are the source of supernumerary rainbows. The smaller the raindrops, the stronger the supernumerary bows. And if the drops are the right size, the first red supernumerary ring can overlap significantly with the main violet ring. And what do red and violet give? Purple. So as the saying goes, roses are red, violets are blue, and purple in a rainbow is a supernumerary hue. This episode of Minute.
So yeah, only red through dark blue. Once again, when people say violet, violet used to be what we called dark blue. We just now call violet purple. The words changed over time. But purple or pink light is kind of weird. Now, the last thing I want to do about light. We said the speed of any wave is wavelength times frequency. And I keep saying what color is based off what wavelength or frequency the light is. Here's the fun thing. Light has a set speed. To be fair, only in a vacuum. That when light travels through a vacuum, it'll always travel at 3 × 10⁸ meters per second. This number, known as the speed of light, is so important it gets its own symbol, that we use c instead of v. C is known as the speed limit of physics. Nothing can go faster than it. It is of note light does travel slower in a medium, including air or water, that it does slow down slightly. But if you're in a vacuum, the speed of light is a constant. And since the wavelength of times frequency of any wave is the velocity, that means for any electromagnetic wave, its wavelength times frequency is c. And so anything on the electromagnetic spectrum, if you know its wavelength, you know its frequency, and vice versa, because the wavelength times the frequency will be a constant. It will be c, will be 3 × 10⁸ meters per second. And so if I tell you what the wavelength is of a light, you instantly shouldn't be able to get its frequency. And so when we say red versus green light is a difference of wavelength or frequency, it's because they're set values. Then when I say this has a 540 nanometer wavelength, well, if I say it has a 540 nanometer wavelength, 540 e -9, that means it has a 5 × 10⁻14 frequency. They're a set value. I only have 1 minute left, but I am going to quickly do a problem, just because it ends this topic. SUNY Delhi has a radio station. I don't know if you know this. It's WDTU. It's at 107.5 FM. A radio station FM, what that is the wavelength of the electromagnetic wave. Radio waves are electromagnetic waves, and FM is what its frequency is in kilohertz. So 107.5 FM is 107.5 kilohertz. What is the wavelength of the wave? What we know is radio waves are an electromagnetic wave. That means they travel at the speed of light. And it has a set frequency, which is in kilohertz, but I can convert to hertz. And for any wave, velocity is wavelength times frequency. And for light, the speed of light is wavelength times frequency. And if I divide both sides by frequency, I can get the wavelength by dividing this and getting a value. Now note that the wavelength of a radio wave is 2 kilometers. This is why radio waves travel through materials. You get radio waves through a house. It's because the wavelength is so long, it can sneak between atoms and travel through materials. Questions? Okay, we're going to stop there. We'll pick up next class with sound.
Thank you.
Yeah, have a good day.